Hello. For this next video we're going to talk about abstract braid groups. Rather than drawing pictures every single time, the benefit of working with abstract braid groups is we can work with symbols. It saves us a lot of mental overhead. These abstract braid groups are similar to free groups, but we do have a few restrictions on our generators. We say the braid group on n strands, B sub n, is the group generated by sigma I, such that 1 is less than or equal to I is less than or equal to n minus 1, and sigma sub I, sigma I plus 1, sigma I must be equal to sigma I plus 1, sigma I plus 1, and sigma j must be equal to sigma j, sigma I, whenever I minus j is less than or equal to 2. So each one of these sigma i's here we might call swaps. Geometrically, what these swaps are doing is they're taking two subsequent strings and swapping them. So for sigma I here, we're taking the first string, we're putting it underneath the second string, the string immediately following it. For sigma 2, same deal. String 2 goes under string 3. For sigma 3, string 3 goes under string 4. And the inverses are going to be, if we do the swaps, the reverse order. Sigma 1 inverse, we're instead taking the first string and putting it over this second string. Sigma 2 inverse, we take the second string, put it over the third. And for sigma 3 inverse, we're taking the third string and we're putting it underneath the fourth string. The first restriction I'm going to call the three-string relation. I'm going to show this with sigma 1, sigma 2, sigma 3, and B3, but I claim this relation will hold for any group that's a braid group with 3 or more strings, as long as you take 3 consecutive strings. So sigma 1, sigma 2, sigma 1 must be equal to sigma 2, sigma 1, sigma 2. The idea here is, in the first picture, the string that lies on top of all of them is the string that starts off over here, the third string. The first string is going to fall underneath all of the other strings, and the second string is going to go above the first string and below the third string. So to get from this picture over here to the picture over here, what we're going to do is we're going to imagine taking this top string here and kind of pushing it all the way over to the leftmost side of this picture. Notice that the middle string is going to now, as a result, move this way a little bit, and rather than crossing over the first string first, then under the third string second, it's going to cross underneath the third string first, and then after that it will cross over the first string. The first string's not really doing all that much to move, so what this is telling us is as long as you keep the top string on top of everything, the bottom string below everything, that string that's kind of in the middle of these top and bottom strings is kind of free to move left and right. It doesn't matter what order it passes over or under. It doesn't change the underlying structure of this braid. The other requirement is the independent swaps requirement. And the idea here is if we have two strings, the first two strings that swap, and the second two strings that swap, it doesn't matter if I swap the first two strings, then the second two strings, or the second two strings, then the first two strings. Because these swaps require independent sets of strings, then it doesn't matter what order the swaps occur in, provided they happen one after another and nowhere along the way we're touching shared strings. So with this definition, there are a couple of braid groups that don't really follow all of this. So the first one is the trivial braid group, beta sub 1. We say this is just the group on zero kind of swaps, right? There's nothing for this first string to swap with, so you're left with the trivial group. For beta sub 2, what happens here is you get the group generated by just sigma 1. There is no sigma 2, so the 3-string relation doesn't really occur. So it turns out this one is the free group on one element, which is isomorphic to the set of all integers. And what this is doing is it's telling us how many times are we twisting. So this braid here, for example, you might call the element sigma 1 to the negative second power, which, if we're thinking about the integers, this is kind of like negative 2. For B3 onward, the structure becomes a little bit more complicated to describe, and it's best described in terms of generators. So the last thing I want to talk about is we can use this kind of abstract language to prove some identities. We might have an identity like this one here. And if we use a 3-string identity on the first 3 elements here, notice that we get sigma 2, sigma 1, sigma 2, sigma 3, sigma 2. But then, if we apply the same 3-string identity on the second set of 3 elements, then we get sigma 2, sigma 1, sigma 3, sigma 2, sigma 3. And finally, to make these things be the same, we're going to apply the independent swap kind of identity here. So we get sigma 2, sigma 3, sigma 1, sigma 2, sigma 3, as desired. And if we look at this geometrically, maybe you see how the swap occurs, maybe you don't. It's not obvious to me at first glance. But if we're thinking about these 3-string identities, the idea is this string and this string are both on top of everything. So we can imagine them both kind of moving up this way, while the 2 bottom strings don't really get affected. Then, if we follow the second string, we can see the second string is supposed to pass over this first string. That pass happens over here now instead. And the geometric relationship does show this. It's probably easiest if you grab some yarn and tape and create this yourself to play with. More complicated identities can be shown with a few lines of algebra as well. So we do like working with abstract groups, especially when we get to very, very complicated strings. If we have our generator rules, we can work with those identities on paper, or perhaps you can get a computer to simplify things. Now, the one thing I'm not going to prove in this video that I claim is I claim that the generators here are sufficient to get the braid group. You do not need any other generators or any other restrictions on these generators. Any other restrictions you can think of with these types of braid groups that follow with braids come from these 2 relationships. This is proven in the book, Study of Braids, and I will leave the proof there.